Welcome to How to Write a Chess Program in Go, video number 20. Today we will talk about the AlphaBeta algorithm, maybe the most important algorithm for chess programs. If we don't think about the neural networks that are coming more and more, let's say white makes the A3 move here. Black can make A6 or A5 or B6 and so on. In fact, black has 20 moves, and for each of black's moves, white has at least 20 moves. Normally it's up to 30-35. Let's look at the position here. I have this Lopez position, and when we are evaluating this position we know that okay, it's good for white. Let's say it's more or less equal. Now we know that there is at least one good move in this position, bishop b5. Let's say we give that 0 points, equal. And now we check another move, king e2. Let's say we are somewhere down in the search 3, and we already know that bishop b5, it's an okay move. And now we will know that this is a very bad move. For instance, knight d4 check, but black might have other good moves like bishop c5 or d5 or something. But we don't need to know how bad this king move is. It's enough to see that okay, knight d4 check makes life complicated for white. We don't need to know if bishop c5 is even better, because now we know we will never do the king e2 move. So now we know that bishop b5 is better than king e2. What we do here is called an AlphaBeta cutoff, or pruning, or whatever you want. We don't search all the black moves after we find knight d4. So we will look at this AlphaBeta tree. It's something I copied from the chess program wikispace.com. That site will disappear, but it will move somewhere else. A is the root position, the root node. That is the position we are analyzing. A has 4 moves. Let's call them AB, AC, AD, and AE. AB reach a new position, the position B, and AC reach position C, and so on. And we can call B, C, D, and E, they are children to A. So A is a parent of C, for instance. If we go down the tree, it's the same thing. We can say B has 4 children, F, G, H, and I. And of course B is parent to them. We can also say that B, C, D, and E, they are siblings. They have the same parent. And the same for F, G, H, and I. They have the same parent. They are siblings. Every child has only one parent. This is a strange family tree, but chess program is strange. So everyone has only one parent, except for the root node, of course. Root node A is on ply 0. The next level, B, C, D, and E, they are on ply 1. F, G, H, I, J, K, L, M, they are on ply 2, and so on down in the tree. The numbers we have in the bottom of the tree, F that has 11, 12, 9, 7, those numbers are evaluations. So F has a leave node that gives 11 or 12 or 9 or 7. When we are searching the tree on the top node, we try to maximize. We try to get as high value as possible. B, on the other hand, is trying to minimize its value. And F is trying to maximize. So every even ply they maximize, and every odd ply they minimize. So they can be in conflict with each other. In this tree we have a lower and upper bound, or I should say every node has a lower and upper bound, alpha and beta. If you are on an even node, or even ply I should say, a node in an even ply somewhere down in the tree, let's say you are on ply 10 or something, then you know that your parent is trying to minimize and you are trying to maximize. And the parents will send down to us an alpha and a beta value. And our parent will say that, okay, here's a beta value. If you exceed that, then I don't like you, because I minimize. I have another child who give me beta. And if you have a higher value than that, you can stop searching. I don't want you. The parent has also a parent, a grandparent, our grandparent. So the parent and the child, they are in conflict. But the grandparent and the child, they have the same goal. They want to maximize, if we are talking about even plies. And the grandparents sent down an alpha to our parent and said, if you are going under this value, I don't want you, because I have another child who gives that, and I'm trying to maximize, and I don't accept anything under alpha. On both levels we have an alpha and beta value, but we treat them a little bit different. I mean, if an even number ply get a value under alpha, we just skip that and go on with the next child and try to find something better than that. If we have a value over than beta or more, then we need to stop, because then we are too good. Our parents don't want that. And on odd number plies, it's the same thing, but okay, I have a value over beta, I don't care, I just go on with the next child. But if I have a value under alpha, then it's disaster, I need to stop. Or it's not disaster, I did very good, but disaster for my parent. I need to stop, and you can call that an alpha cutoff. And when on even ply exceeds beta and stop, we can call that a beta cutoff. These alpha beta represent a window that every node need to keep track of, and every node is sending down to its children. Let's say we are on even ply and we get something better than alpha, but not better than beta. Then we can adjust our alpha value up to this so far best score. So the window gets smaller and smaller. This alpha beta window gets smaller and smaller the deeper we go in the tree. During a search, we always start with the left side of this tree. So A start with the AB move and gets B. B starts with the BF move and we get the position F. And F have 4 moves that are evaluated to 11, 12, 9, 7. And F is an even ply. F tries to maximize. So F will select the child with the highest number. That's 12. So F's value is 12. That is the best F can think of to get. 12 is backed up to B, so now B has an alpha value telling the next child, G, that I don't want anything higher than 12. So I said wrong. 12 is a beta value for B. I don't want anything higher than 12 because I already have a child, my child F, that gives me 12. And I'm trying to minimize. So G start to search, find first move that gives 15, and that exceeds beta. That means stop, don't search more, because B, my parent, will not accept that. And the same, B try next child, H, and B wants something lower than 12, but H is in conflict with the parent. H find 13 and don't want lower than that, so need to stop and send back the value of 13, and B will just ignore it. And the same with I will get 17 and stop search. All these stops are beta cutoffs. And it's sent up to B, and now B has the value 12, and that is the best B can get, and that value is sent up to A, and now A has an alpha value that is 12. That means A don't want anything lower than 12. And that is sent down to C, that no, okay, I cannot get anything lower than 12, and so on and so on. This is how the search is done. In the code, it's a bit complicated to keep track of who is maximizing and who is minimizing. So instead, every node sends negate its alpha and beta value down to its children, and the children replies with negating its best score, and the result is that everyone on every node on every level now can maximize its value. So we don't need to think about minimizing anymore. Everyone is maximizing, and the only cutoff we have is a beta cutoff. So it's in a way it's simpler, but the result is exactly the same. This took much longer than I thought, but at least we can start a little bit of coding. So let's start with some const and variables that we need. We need to count the nodes so we know how much nodes we are visiting. So, and a principal variation list. It's good to have the nodes that are our main line. So that's the list of moves. We can add a move to the list. Just append, like so. And this should actually be a method. So, and we copy so we can do some other stuff here. And here is a list of methods to the principal variation list. We can add moves to the list. We just append. We can clear the list, of course, And we can add another principal variation to that list. So in a way we combine lists, and that is because we are picking up lines from our children, the children that we select that we think is the best one. And catenate is that we put our move on top and we take out the list from the children. And we can make a string of it, so it's possible to print. All this will be clear when we are using it. This was a very tiny little start of the AlphaBeta coding, but it was something. Okay, we continue next time, and until then, have a good day.